Today we are going to introduce the random variable concept for the first time, and it is not very hard to understand. Actually, it is something simple. And from this point on, until the end of the lecture, we are going to work on random variables. So this is not just a one-time topic. This is the main dish of the course. So we are going to learn about the random variables. So far, we have learned about the probability concept, how to calculate the probability of events through conditioning and the independence of the events. And from this point on, we are going to work on random variables, which is a quantified representation of the outcomes of a random experiment. Okay, so we are going to give a definition, and we are going to spend a little time on that definition. So we need to understand the concept of random variables mathematically. Then we are going to say that we classify random variables into two classes: discrete random variables and continuous random variables. These two things, discrete and continuous random variables, are modeled completely differently. So they have a different modeling, and please do not confuse these things, which means at this point, you need to understand the difference between the discrete random variables and the continuous random variables correctly. So you need to identify which one is which. Then, in the end of the chapters, we are going to talk about some important identities on expectation and variance. However, of these, you need to learn about the expectation and the variance concept. So what is a random variable? Let's just consider an experiment with sample space S. Remember, a sample space was a list of possible outcomes of that experiment. Now, in some of the experiments, we define the sample space in qualitative terms. So we basically write, for example, what is the condition of weather today? And you can give the list of possible outcomes of this experiment. You can say sunny, rainy, foggy, etc. Okay, you can give qualitative outcomes. However, frequently we are interested in some quantitative function of the outcome as opposed to the actual outcome itself. So we are interested in the, for example, temperature of the atmosphere. So this kind of quantitative terms, we are much interested in this kind of thing. So instead of considering the qualitative outcomes, we convert them into quantitative terms. We just label them with a quantitative value. Actually, because of that reason, we define the random variable as a real valued function on the sample space. So that function converts the outcomes into real numbers. And in that sense, my friends, as I can define different functions on the outcomes, I can define different random variables on the same sample space. Now consider this experiment. When you toss two dice, remember, you have 36 equally likely outcomes in the sample space, and though these outcomes are written as integer values, you cannot just quantify them. I mean, you cannot say, for example, when you get a 3/4, it is larger than 5/6. I mean, this is just an outcome. 3/4 is an outcome, 5/6 is another outcome. You can say that 3/4 summation is lower than 5/6. However, you cannot 5/6 is greater than 3/4. Maybe 3/4 is greater. Maybe 3/4 is better. So these are just qualitative outcomes. We have 36 equally likely outcomes, and they are qualitative outcomes. They cannot be represented numerically. However, you can talk about the sum of two dice. If you talk about the sum of two dice, then you can convert each outcome into a quantitative value. For example, 3/4 can be converted into 7 as the sum of two dice. Or 5/6 can be converted to 11 as the sum of two dice. Or you can define another random variable, absolute difference between two dice. So when you get 3/4, the absolute difference between two dice would be 1. Or when you get 5/2, the absolute difference between two dice would be 3. So in that case, you can get different values for these random variables at different outcomes. So this is dependent on how we define the function itself, how we define the random variable itself. However, as you can see, on the same sample space, I can define different random variables. Another random variable is t, which is the maximum of two dice. If you get a, for example, 2, 2, okay, if you get a 2, 2, 2, in that case, you are going to have t equals to 2. The maximum of 2, 2 is 2. Or if you get, for example, 4, 1, the maximum of 2 dice is 4. You can define another random variable, w, the minimum of 2 dice. For example, if the outcome is 3, 5, then the minimum of 3, 5 is 3. If the outcome is 6, 6, the minimum of 2 dice is a 6. Now, my friends, as you can see, I can define as many random variables as I can using mathematics. But what is the common property of these random variables? I will list you two common properties. The first property is that they are defined on the same sample space. And the second property is something irrelevant, but all these random variables are denoted with capital letters, my friends. This is important because in this course, we are going to define random variables with capital letters. So when you see a capital letter, it corresponds to a random variable. Do not forget about it. Now, you know, the value of the random variable is determined by the outcome of the experiment. So if, for example, the outcome is 2, 3, the sum of 2 dice, the random variable which represents the sum of 2 dice becomes equal to 5. If the outcome is 2, 3, the random variable is going to be 5. So the random variable's value is determined by the outcome of the experiment. And because the outcomes have probabilities and the events have probabilities, therefore, the random variable to take a certain value will have a probability as well. So random variables will take possible values with respect to the outcomes of the underlying experiment, and they will take these values with respect to the probabilities of the corresponding events. Now let us describe this situation. We let x denote the random variable, which is defined as the sum of 2 fair dice, and for x to be equal to 2, for the sum of 2 dice to be equal to 2, the outcome should be definitely 1, 1. So this subset, this single element subset, corresponds to the event of x being equal to 2, the random variable being equal to 2. And this event has probability of 1 over 36. Therefore, the probability of this random variable to be equal to 2 is 1 over 36. Similarly, if the random variable is supposed to be equal to 3, then this is either possible by the outcomes of 1, 2, or 2, 1. So this event is defined as the sum of 2 dice being equal to 3. This event also makes x equal to 3. Therefore, the probability of x being equal to 3 is 2 over 36. So I am not going to explain all of them, so I'm just going to skip to another one. The probability that our random variable being equal to 9 is what? The probability of the sum of 2 dice being equal to 9, and it is possible with one of these 4 outcomes, and the sum of 2 dice being equal to 9 corresponds to this subset as an event, and this subset, my friends, has the probability of 4 over 36. So you can see, if we define the random variable based on the underlying random experiment and its sample space, we can determine the corresponding events for each equation of the random variable, and these corresponding probabilities will give you the probabilities of these random variables to take different values. You know, the sum of 2 dice can be 12 at maximum in the case where we get a 6, 6, and it can be 2 at minimum, and it can take different positive integers between 2 and 12 inclusively. Now, as you can see, each outcome represents to a value. For example, 1, 4 represented by 5, and 4, 1 is also represented by 5. 3, 4 is represented by 7, 5, 2 is also represented by 7. So you see, each of these outcomes correspond to a value for the random variable. So how do we define the random variables? As a function that is defined on the sample space. So remember, the sample space of a random experiment is a set of all possible outcomes of that random experiment, and x is a random variable, which is a function that relates each of the outcomes in the sample space with real numbers. And then we define the probability. Probability is a reflection of the real numbers on the unit interval. Okay, so in order to understand this relationship better, we are going to solve an example. So suppose we toss two fair coins and we denote y as the number of heads appearing. Y is the number of heads appearing in two fair coin tosses. So if you toss two fair coins, what is the minimum possible value for the number of heads appearing? Obviously, it is 0 because, I mean, if you get two tails in these two flips, it is possible, then the number of heads appearing will be 0. Now, if you get a single head, then y is going to take one value. And if you get two heads in these two coin flips, then y is going to two values. So what values y can take? We know that the possible values that y can take are 0, 1, and 2. And with which probabilities y can take these values? Let's check it. Just like in the previous example, in the dice example, we say that the probability that y is equal to 0 is possible with the probability of getting a tail. Because when we get a tail, y is going to be 0. Number of heads is going to be 0. And the probability of y being equal to 0 is simply 0.25. The probability of y being equal to 1 is the probability of getting exactly one head. And this is only possible with these two outcomes, th and ht. You know, each of these two outcomes has 0.25 probability, and therefore this event, this subset, has the probability of 0.5. And finally, the probability that y is equal to 2 is the probability of getting two heads, which is 0.25 again, assuming that we have fair coins. Remember now, when you toss two fair coins, you have a sample space that consists of 4 equally likely outcomes. Each outcome here has the probability of 1 over 4. And now let's define our random variable. Our random variable y is defined as the total number of heads appearing. Now, how many heads appear in this first outcome? 0. So random variable y relates this outcome to 0. So random variable is a function of the outcomes in the sample space into the real numbers. It's a projection of the outcome to the real numbers. This random variable is equal to 0. This function becomes equal to 0 when the outcome is tt. If the outcome is either th or ht, in these two outcomes, the projection is on 1. So the random variable becomes equal to 1 if the outcomes are either th or ht. And if the outcome is hh, there are two heads appearing in this outcome. The reflection is made onto 2. Finally, we are going to define the probabilities. Now, 0 has the probability of 0.25. So the probability function reflects 0 on 0.25, reflects 1 on 0.5, and reflects 2 also on 0.25. So random variable is a projection of the outcomes in the sample space into real numbers, and probability this time is defined over the subsets of real numbers as a projection onto the unit interval. So this is how we define random variables and the probability on these sets. My friends, everything in the mathematics is either a set or a function. So a sample space is a set, a random variable is a function. Real numbers is a set, probability is a function, and unit interval is also a set. Okay? And these random variables and probabilities are functions just reflecting the elements of one set into others. So when we are talking about the probabilities of events or probability of a random variable to take a value, we are actually talking about a function here. This is mathematical modeling of these events. Obviously, not every time we are going to draw pictures like this, Once we understand the random variable concept, we are going to solve the questions directly without even looking at the underlying sample space. But at these earlier points, we are just going to focus on the underlying sample spaces. Now moving to the next question. Question number 2. Suppose that our experiment consists of tossing 3 fair coins. So we are going to make this complicated a little. This time we define y as the number of heads that appear again. However, this time we have 3 coin tosses. So what are the probabilities of random variable y on the values that it can take? Again, a similar question is asked. So the question firstly asks, what are the possible values y can take? And secondly, it asks, what are the probabilities for random variable to take on these values? So we are going to do the same. Again, we have a sample space. As you can see, our sample space here in total, we have 8 possible outcomes in our sample space. All 3 can get a head, 2 of them can be heads, and 1 of them can be tail. 2 of them can be tails, and 1 of them can be head, and all 3 coin flips can be a tail. So there are 8 possible outcomes which are equally likely in the sample space, and our random variable y can be 3 at maximum when all outcomes become a head, and when all outcomes are tails, our random variable gets the lowest possible value, which is 0. Our random variable can take 1 and 2 as well. So the probability of our random variable to take 3 is the probability of getting 3 heads, which is 1 over 8. Probability of our random variable being equal to 2 can happen with these events. If we get 2 heads and 1 tail, so in any of these 3 outcomes we have 2 heads and 1 tail, then our random variable will be equal to 2. Therefore, the probability that y being equal to 2 is 3 over 8. So by 3 over 8 chance, or by 0.375 chance, we can get 2 heads. What is the probability of y being equal to 1? Or in other words, what is the probability of getting 1 head, exactly 1 head in 3 flips? So it is only possible in one of these 3 outcomes. Again, the probability is 3 over 8. Finally, the probability of y being equal to 0 is 1 over 8, because it is only possible in one of the outcomes where we get all 3 flips as tail. Now, my friends, the summation of these 3 probabilities, as you can see, is 1. We have 4 possible cases for y. Y can take on 4 different values with 4 probabilities, and these probabilities sum up to 1. Now, let's solve another example. This time, again, we are going to think about an underlying sample space, but it is going to be a little complicated than the previous examples. In an urn, there are 20 balls, 3 of which are golden. Okay, there are 3 balls golden and 17 ordinary balls. We pay $1 and randomly choose 3 balls from the urn. We will win respectively $1, $50, or $1,000. If we select a single golden ball when we select 3 balls. If we choose 2 golden balls in this tree, we will win $50. And by chance, if we choose all 3 golden balls, then we are going to win $1,000. Okay? So capital X as a random variable denotes the profit from this game. My friends, let's check the possible profits for this game. Now, do not forget about that. Your initial payment is $1. If you choose 3 balls, it is possible that none of them to be golden. I mean, you can choose from the remaining 17 balls by chance. In that case, your profit will be -1 because you will lose your $1. You are not going to win anything and you are going to lose your $1. So your profit will be -1. If you choose exactly 1 golden ball, in that case, you are going to break even, which means you are going to invest $1 and win $1 again. So you are going to break even and your profit will be 0. If you choose exactly 3 golden balls, when you choose 3 balls, then your profit will be $49. And if you choose all 3 golden balls by chance, then your profit will be $999. So the question is this: what are the probabilities of X on the values that it can take? We have already determined the possible values of X. The question is, what are the probabilities? Now, my friends, what is the probability of your profit to be equal to -1? What is the probability of x being equal to -1? How can you calculate this probability? This experiment consists of choosing 3 balls out of 20, and it has 20 choose 3 possible outcomes. They are all equally likely. In how many of these outcomes we choose 3 ordinary balls and 0 golden balls? We determine this by the basic principle of counting. We say 3 choose 0 times 17 choose 3. And the numerator will bring you a 680, and then denominator will give you a 1140. So this ratio is the probability of losing your $1, the probability of having -$1 profit. Breaking even or having 0 profit, it happens by selecting 1 golden ball when you choose 3. So again, the sample space consists of 20 choose 3 possible outcomes. However, the cases where we choose exactly 1 golden ball is 3 choose 1 times 17 choose 2. So we choose 1 golden ball and 2 ordinary balls. And the number of cases that gives us this is 408. Therefore, this value gives you the probability of your profit being equal to 0. The probability of your profit being equal to 49, or the probability of x being equal to 49, is again calculated in the same manner, but this time in the numerator you write 3 choose 2 times 17 choose 1 because you select 2 golden balls. And this ratio gives you the probability of this event, 51 over 1,140. And finally, you are going to win $999, or you are going to make this profit if you choose all 3 golden balls, but none of the ordinary balls, which happens with only one case, right? So there is only one case that makes this out of 1,140 possible cases. Only one of them will make you win $999. And therefore, you can see the probabilities of all these realizations of this random variable are calculated. Or random variable, or in other words, or profit can take 4 possible values with these probabilities. And again, you can check, my friends, these probabilities will sum up to 1. So if you sum 680 with 408 and 51 and 1, you are exactly getting 1,140. So the question here is this. We may have understood how to calculate these probabilities, but would you play this game? The main question is this. Would you play this game to make money? I mean, if you have enough dollars, every time you play this game, you pay $1 and play it. Sometimes you lose that. Sometimes you break even. Sometimes you will gain $49. Sometimes you will gain $999. Would you play this game is a question that we may answer in the end of today. So in these previous examples, the random variables that we have talked about were actually all discrete random variables. Okay. However, there are some continuous random variables which can be used to model real life amounts. So we are going to classify random variables into these 2 classes, discrete and continuous random variables. And these random variables are both conceptualized and modeled differently.